Hello, I'm Ron Kenett. It's a real pleasure to be in this joint QSR ENBIS session. The talk I'm going to give involves generalization and interpretation. And the point is that there is a lot of similarity between these two terms. So this is what I'm going to talk about. What do we mean by to generalize? We have some data. We have a ridge here. We have some clear view of that ridge. There are some additional mountains in the background. And we have the ability to imply how these hidden mountains look like based on what we see. That's a sort of generalization. Generalizability is one of the 8 dimensions in the information quality framework that we proposed a few years ago, which deal with what you need to consider if you want to get information quality from some analytic work. So you have some data, you're doing some analysis. What's the information that you generated? Part of that is related to your ability to generalize the findings that you reached. The concept of information quality involves a goal, a certain data set, a certain method of analysis, and a certain utility measure. More details are in this book, and there's a talk here you can look at. So I'm not going to give an information quality talk. I'm just going to refer to generalizability. We have several modes of generalization or generalizability. They involve hard data. They also involve soft data and intuition. And statistics is typically about inferring from a sample to a population, but there are other ways that people generalize. For example, with mechanistic models, you have the physics, the mechanics that has been translated into mathematical mechanistic models, and this is a method of generalization. Predictive analytics is a sort of generalization. You're trying to use existing data to predict future data. The trick there, of course, is to have a holdout set so that you have training data and validation data, and you can check the model that you developed using the validation data, and that gives you some sense of the generalizability properties of your model. And then there are more formal ways of generalizability. One of them is called transportability. I will mention that. So we have some current data, we have some intuition. We want to say something about the population from where the data was drawn. We want to say something about future data. We want to say something about a related population, not exactly the one we took the data from, but a related one. These are the goals of generalization. Judea Pearl dealt with that. That's a paper called Generalizing Experimental Findings, and he talks about transportability. So these are terms that you will find in this context. And in achieving the ability to generalize, Pearl imagined this three-legged, 3 steps ladder, where at the bottom you have the ability just to talk about associations. Then you have interventions. He's using graphical models for that. People can use randomized control trials for that. And then there's a whole domain of counterfactuals. These are fictitious experiments that you conduct. As you go up on this ladder, your ability to generalize is enhanced. So here are some slides from Judea Pearl. He talks about the structural causal model. This is a graphical model. We have endogenous and background variables. We have a function that determines the endogenous variables. And it could be a linear model. And then we have a distribution on the background variables, and the combination of the background variables and the function is giving us the distribution of what we observe. And the example that Pearl is using, I've enhanced it a bit, is, for example, considering study conditions. This is condition A and condition B. Condition B seems better. The study condition affects your score. Why? But there's another thing that can affect your score, which is the study time. And now we have some overlap because the study conditions also affect the study time. This is a more convenient setup for studying. So you're going to spend more time just because of the study conditions. So the way this is set up, this is a graphical model. X affects Z, and X affects Y, and Z affects Y is through these equations. X is a random variable, Z is affected by X, and Y is affected both by X and Z. So in the example that Pearl gives, we have data. We assess alpha, the parameter of X, to be 0.7. We assess beta, the parameter of X on study time, to be 0.05. And we assess gamma, the effect of Z on Y. And we're looking at Joe. Joe has X half, so he's in a situation where the study conditions are somewhere in between these two options. He's studying for 1 hour, and the score he gets is 1.5. So what do we mean by generalizability? What would happen if instead of 1 hour, Joe studied 2 hours? Can we say something about that? Can we interpret the model to tell us something about what happens if the time is doubled? So what we're going to do is use these equations, and what we're going to have is the data that we originally had. We're going to consider the effect of doubling study time as not related to the study conditions. This is called mutilating the graph. So we're going to break this relationship. And under these new conditions, we're going to figure out that instead of 1.5, the score will increase to 1.9. This is the do calculus of Pearl. Then we can have additional questions. What would be the score of Joe if he went to treatment being 0, namely the unfavorable conditions, and the study time being 1? So we basically repeat that type of exercise, and we see and we can compute the results. This method, based on the graphical models, gives us an option to generalize. What can we do with generalization? We can take a study done in LA and adapt it to the situation in New York. So LA might have a younger population. We can calibrate the results to the population age in New York. So we can take the results we found in LA and apply them to New York. In an industrial setting, we have a wave soldering process. We have an extended wave soldering process. This is a scale-up process, and we can do the same thing. So here we can generalize from the experimentation that we've done here to the larger process. We have the example here on the study in LA. We have the causal structure. We apply the do calculus, and now we can say what will happen if we move the background context. We transport the formula to in this case from LA to New York. Here are some links if anyone is interested. So this was generalization at the version of Perl. There are other versions of generalization. This is a paper by Raja, Gires, and colleagues. They basically consider generalization solely on the basis of misclassification error, and they get bounds on the misclassification error between the training set and the validation and the test set, the validation set, based on some properties of the data. This is a course I'm giving in Italy, and in that course I'm spending a lot of time on causality and generalizability. So now interpretability. What do we mean by to interpret? ENBIS had a fantastic workshop titled Interpretability for Industry 4.0. We had 3 sessions, one interpretability via random forests, another on interpretability via additive models or generalized additive models, and the third one on interpretability of big data in Industry 4. In that context, things that were discussed were SHAP. SHAP is Shapley additive explanations. Shapley is this guy, Lord Shapley, Nobel Prize. He used to work for Rand. He worked on game theory, and this is more of a feature selection approach. In other words, when you have the features A, B, C, or combination of them, what you get. So the SHAP value, which is used to identify the interpretability of models, this is the original paper by Landberg, is really about feature selection. Sobol, Meirovich Sobol, he devised methods of sensitivity analysis. Okay, so this is interpretability in the sense of the sensitivity, the variable importance in models. Sensitivity analysis is also the topic of Andreas Altelli. He gave a talk at ENBIS in Budapest in 2019. You can watch it. It's a great talk. So interpretability also, like generalizability, gets to be interpreted in different ways. Another approach that you might find interesting is called Granger causality. Clive Granger, another Nobel laureate. You have a time series. You can make some predictions based on the time series itself. You can add time series of covariates if the parameters of these covariates are significant. Then the prediction is based on past data. Then these covariates are called causal in that they add to the predictive value of your model. So to wrap up, we have 2 concepts, generalizability and interpretability. Generalizability can be done with intuitive methods. It can involve mechanistic models. It is extended through structural causal models, and it can be applied in the context of neural networks. Interpretability, if you go through the literature, is about SHAP, which refers to variable importance. Sobol indices also related to variable importance. Sensitivity analysis and Granger causality, these 2 domains should be merged. And the point is that perhaps some work on combining them and looking at a common understanding of what is intended here would be useful. So thank you very much for your attention, and I'll be glad